Let's get this video started. This is video 10A, and it's going to review the slides from week 9, that previous week. So the topics for this week that we're going to learn about is work. So the assignments for this week, there is a homework assignment, a notebook check, the power activity, and there is an energy quiz that is due that Friday, March 26th at 11:59 p.m. The only announcement I have is make sure you get that energy quiz in. Just make sure you get it in, and I'll grade it over spring break as well. So if you need to do it over spring break, go ahead. I'll grade it when I get back. And there is no big question for today, but I always put up Sir Isaac Newton just because he did his best work during quarantine. All right, so remember there's a weekly task list. Just watch all 3 videos. We're not on a synchronous lesson anymore, but that has been replaced by a notebook check. There is an activity, so that's our lab activity or lab activities, and there is also a homework assignment. There are codes in each video. There's 2 codes. There's one that's written and there's one that is a verbal code. Each of them is 3 numbers. It's random. You cannot guess that. You need the codes in order to move on with the assignment. So let's just review. So this is what we learned last week. So we talked about why a ball won't bounce to the original starting height, and we did the destroyed energy lab. And we said we know the law of conservation of energy. We know that energy can also transform or change into another form of energy. So there is a difference between energy change and energy transformation. When energy changes, the total mechanical energy will increase or decrease. And how I remember this? If energy changes, then this number right here, the mechanical energy, that will change as well. Now, if energy transforms, it's going to go from kinetic to potential, but the total mechanical energy doesn't increase or decrease. So right here, if this is if your energy is transforming, I'm just going kinetic, potential, but this number remains the same. So we talked about why a Newton cradle can't go forever. So as a Newton's cradle is going, energy is being transferred across it. So I'm going from object to object. Now, energy is being transformed as those ball bearings are falling down. It's going from gravitational potential energy to kinetic energy, but the mechanical energy remains the same, right? Same thing as when the ball is going up, because it's going from kinetic to gravitational, but my mechanical energy remains the same. Now, energy being changed. So this is like energy being lost to the outside world. Every time they hit, you're going to lose a little bit to sound, to like air resistance, to heat, that internal friction. And also, when the first thing you do is you lifted it, well, that's going to increase your mechanical energy. Because you start with no mechanical energy, you lift it, and it's going to increase it. So, and then every time it hits, you lose it to sound, that's going to decrease that mechanical energy. So we talked about eliminating air would eliminate that energy loss to sound and air resistance, but it wasn't that much because a lot of it's just lost to heat. All right, now we talked about what causes energy change and energy transformation. That's conservative forces that transforms energy. Energy is stored, path independent, and examples are gravity and spring force. Now, non-conservative forces, they change energy. The energy is dissipated as heat, sound, internal energy, etc. It is path dependent, and examples are going to be friction. That's the big one, but all other forces are, but mostly for this class, we're talking about friction. So let's look at this, right? Let's look at the person skiing down a ski slope. Now, as the skier is going down the ski slope, you'll notice that the total mechanical energy, that green bar, doesn't change. So that energy is transforming because I'm going from gravitational potential energy to kinetic. So gravity is pulling that slider down. So if gravity would be a conservative force because it's conserving that energy. That mechanical energy isn't increasing, it's remaining the same. So now if we look at that unpacked section of snow, the skier hits the unpacked section of snow, the mechanical energy is going down. So the energy is going to be changing. So friction is what's slowing that skier down. Now, friction is a non-conservative force because as it hits that it's not conserving the mechanical energy. It's being lost to the outside world. All right, so those are the links for that day. Then we talked about work. So work is the act of changing or transforming the energy of an object. So the unit for work is joule because you're just affecting that energy. You're either changing the energy or you're transforming that energy. And we showed this with the stair challenge. So the challenge of this lab is to pick the person in your lab group who can do the most work by running up the stairs as fast as they can. And it said, try to beat Mr. Cardoza and Bob. So that was the big anvil. So If force is applied, that object will change motion or accelerate. If impulse is applied, then the momentum will change. Now, if work is done on an object, then the energy of that object will change or transform. So, work is a scalar quantity, right? It's the product of the force times the displacement times the cosine of the angle between them two. So it is a scalar quantity, so it is the absolute value of the force and absolute value of the displacement. And then the cosine in between those two. Now it looks confusing, but it's going to get a lot easier. So to do work, two conditions must be met. A force must be applied, and that object must move in line with that force. Now perpendicular components of the applied force to displacement do no work. It's because of that cosine. Now, if we simplify this, positive work is done on an object if the force is applied in the direction of motion. Negative work is done if the force is applied in the opposite direction of motion. No work is done if the force is applied perpendicular to motion. So we did that ball toss. Now the person that throws the ball is applying the force in the same direction of the motion. So that person is doing positive work. Now the person that's catching it is applying a force in the opposite direction of motion. They're slowing it down. So that person's going to be doing negative work. Now, in general, if the work done on a body is positive, then the body will try to gain speed. If work done on a body is negative, then that body will try to lose speed. Now, let's get back to the original question. Who won that stair challenge? So you'll notice that this was the template that I had. So to calculate the amount of work you did, multiply your weight in pounds by 4.45 to get newtons, then multiply that number by 3.5 meters. Because remember, gravity is a conservative force. It's path independent. Now, we didn't need time. There's no time in that equation. And like basically what it is that if you're applying a larger force, your weight up that same distance, you're going to do more work because that was the challenge. And that's why I was carrying more weight, because I said I was giving myself a handicap, but in reality, I wasn't. I was giving myself an advantage. So let's talk about lifting an object then, right? So if someone is lifting the weight up off the ground, then you're going to have a couple of different forces acting on it. You're going to have gravity and that applied force by that person. So what happens is that the person is going to be doing positive work because it's moving up and that person's applying a force upward. Now, gravity would be doing negative work because gravity is applying a force down and it's moving up, opposite directions. Now, as the barbell, if that person holds that barbell at the waist, that person is doing no work. It's not moving. Same thing with gravity. Now, if that person drops the barbell, well, that person's not doing any work because that person's not applying a force. Now, gravity is going to be doing positive work now because it's moving down and gravity is going down. So gravity can be positive, negative, or zero work depending on the motion of the object. So how much work is being done on a pendulum? So what you should have gotten out of this is that there are two forces that are acting on this pendulum as it's swinging, the string and gravity. As it's swinging down, gravity is doing positive work. It's speeding it up, right? And as it's swinging as it's swinging up, gravity is doing negative work because it's slowing it down. Now, at the very bottom, that equilibrium point, gravity is doing no work. Now, the string does no work on this the pendulum because at every single point, the string is applying a force perpendicular to the motion of the pendulum. All right. So does the sun do work on the earth? So here's the thing. This one is a little advanced, but the sun speeds up and slows down, and it reaches perihelion and aphelion. So perihelion is the closest that Earth gets the sun, and aphelion, which is the farthest. So just like that pendulum, the Earth speeds up and slows down. Now, as it speeds up, the sun is going to be doing positive work. Now, as it slows down, it's going to be doing negative work. Now, at perihelion and aphelion, those are the exact moments when the force of the sun is being applied perpendicular to Earth's motion, and it's going to be doing no work. Those are the links for that day, and this is the video 10A. This is the written code. It's 578. I recommend you write that down somewhere. So we're going to be learning about power this week. So this is the video that will help you learn about power, and the verbal code is 778. I say that again, the verbal code is 778. So we're going to have a simulation this week, and you're also going to have a challenge. This is a fun little thing we do before spring break. It's called the Big Mac Challenge, right? You're going to see how long it takes you to burn off a Big Mac by lifting a Big Mac up to your mouth to eat it. All right, So those are the links for this week. And just as a final thought, remember there is too much unknown in the universe to take a break from learning. Get out there and question everything.